Hi guys, please like, share and subscribe and contact this number if you want lectures related to any CM, CS or CB subjects. Thank you.
Okay. So here I want to discuss this topic related to payment streams, their discounting and accumulation. Okay, because students say that they face issue with this. So let me make this clear, like how does this exactly work, right? I'll discuss this question, which is subject CT1 April 2010 question number 11, and I'll just discuss the third part of it. Okay, so a continuous payment stream is received at a rate of 10 times e to the power of 0.01 t units per annum between time t is equal to 6 to t is equal to 10. Calculate the present value of this stream. Okay, and this is the value of delta that is given, right? So now what is happening is that from time 6 to time 10 you have this payment stream payable. Okay, let's call it rho t. It's being paid at the rate of 10 e to the power of 0.01 t. Okay, let me in fact make this sort of wider. Okay, time 6 to time 10. Okay, fine. Now what we need to calculate is the present value of this stream. Okay, that is the value at time 0, and then we have this force of interest which is given to us. So now how will we calculate this? Okay, what we do is we consider an arbitrary time t here between time 6 and 10. Okay, so if we consider this time t, and if I am to calculate the total value of this stream, I am just adding up the stream without discounting. Let's say I just want to add up the stream, the total value of the stream. So what will be the total money value? I would say that at any representative time t, at any arbitrary time t, the value of the payment would be 10 e to the power of 0.01 t times dt. In a small period of time dt, what I'll do is I'll essentially take a representative time t, and I would divide this interval into small periods of time dt, such that in any period of time dt the payment will be 10 e to the power of 0.01 t times dt. Okay, and now I need to get the total payment, so I'll add this up from time 6 to 10, and this would give me the total value of the payment. Okay, so it's as simple as that, right? Now what I here want to calculate is the present value of the payment. I want to calculate the present value of the payment. This is not the present value. This is, I am just taking in a small period of time, I am saying that the payment will be 10 e to the power of 0.01 t times dt, right? Because the annual payment, the annual rate of payment is this is the annual rate, and this is the small period of time dt, and then for all the t going from 6 to 10, I will just add over it. That is what integration is. It's addition over a continuous time period. So this will give me the total payment. Now if I am to calculate the present value at time 0, how will I calculate that? What I'll do is I'll discount this payment, each of these payments, right? These payments are occurring at different points of time, right? Between time 6 and 10, they will occur at time 6.1, there will be a payment at time 6.2, almost continuously these payments are occurring from time 6 to 10, right, at every moment. And the discounting rate from time 6.1, let's say I want to first discount all of these payments to time 6, and then I want to take them to time 0. Okay, so if I am to discount this payment from time 6.1 to 6, the discount factor will be different. If I am to discount it from time 8.5 to 6, the discount factor will be different, right? So discount factor will change with the value of t, which is varying from 6 to 10, right? So what will be the discounting factor from time t to time 6? That is the question. T is a representative time. I want to discount from time t to time 6. What will be the discount factor? It will just be V 6 comma t. This will be the discount factor that I'll use. Okay. This will give me, if I just consider this part, it will give me the present value of this payment of 10 e to the power of 0.01 t times dt at time 6, just this one payment, and then I'll add over all the possible values of t from 6 to 10. Okay, so this will give me the total present value at time 6, and then obviously this entire thing I want to take it to time 0, so I'll multiply it with v 0 comma 6. What I want you to note here is that t is a representative time. What does that mean? It means that t represents all the moments of time from time 6 to 10. It represents 6.1, 6.2, all the way up till all the way up till 10, right? And at each of this moment, I'm considering a payment. I'm considering a small period of time dt, where I'm considering the payment to be 10 e to the power of 0.01 t dt. This is the payment that is happening in a small period of time at every moment, which is represented by t. So then I'm taking each of these payments and then I'm discounting them to time 6 and then adding them up. And that is what gives me the present value of all of these payments from time 6 to 10 at time 6. And then obviously I can further discount it to any time I want. In this case, it's 0. Okay, that is how I'll go about it. Now, if I am to evaluate this, how will I do that? From time 6 to 10, 10 e to the power of 0.01 t. What will be v 6 comma t? First of all, I would need to see what is the force of interest that would apply in this region. So this is when t is greater than equal to 5, it's 0.05. So after 5, the force of interest is a constant 0.05. So from 6 to t in this region, it will be 0.05, right? So this will become e to the power of negative integral from, where am I discounting from? 6 to t, right? This is the region, right? And what is the force of interest? It's 0.05. Okay. Then you have a ds, okay, because there is a limit t in the limit, so I'll have to write it in terms of s. So this is basically the discounting factor that discounts this payment of 10 e to the power of 0.01 t dt from time t to time 6, okay, and t is a representative time, so t will vary from 6 to 10, and for every t this discount factor will be different. Okay, that's why we are not using fixed limits here. We are not saying 6 to 10 here, because this is just the discount factor from time 6 to 10. Okay, but here we are not trying to discount from 10 to 6. We are trying to discount this arbitrary payment 10 e to the power of 0.01 t dt, which happens at this representative time t 2 times 6. Okay, and that's why as the value of this t will vary, this payment will also vary, because it's a payment stream, right? So the value of the payment itself will vary, and so will the discount factor as well, because the payment which will happen at time 8.5 won't be discounted at the same rate as the payment which will happen at time 6.5, and that's why this limit has to be from 6 to t and not 6 to 10. This is the part where people get confused. And then obviously outside you have v 0 comma 6. So this is straightforward. So how will you discount from 6 to 0? For 1 year, you need to discount from 5 to 6 for using the interest rate factor or force of interest of 0.05 ds, and then you will discount from 5 to 0, so it's negative 0 to 5, 0.04 plus 0.02 t. dt. Okay. In fact, you can also write this as in terms of t, because obviously these terms are outside, right? So this is how you solve such questions, and obviously further you can solve it yourself. I just wanted to like write this integral and this is explain this part specifically because this is where students get confused. There can be an alternative formulation as well. What you can do, instead of discounting it to times 6, you can also discount it to time 5 or times 0. Okay. So how will that work? Let me show that formulation to you. So another way to do this question is, and let me talk about that. Okay, what you could have done is that for any arbitrary time t between or greater than equal to 5, what will be the discount factor for this time? The overall discount factor v 0 comma t can be written as discounting from 0 to 5 using this discount factor 0.04 plus 0.2 t. And then discounting from, or in fact you can write this in terms of s, right, and obviously ds here, and then from time 5 to t by using this factor of 0.05 s. ds, because this is a constant. So this was actually the first part of the question, derive and simplify as far as possible the value of vt, right, which will have two parts to it, where t is between 0 and 5 where t is greater than 5, right. So this vt for t greater than equal to 5 needs to be derived like this, right. And once you have this, what does it look like? It's e to the power of negative integral. So if I solve this, it's 0.04 t, sorry, I'm solving in terms of s plus 0.2 s square by 2, right, and I will have to add from 0 to 5 plus, and this is obviously added to this because this is e to the power and multiplied, right. So it would basically get added, which will be 0.05 and you can write t minus 5, right. And if you solve this whole thing, it will just give you e to the power of negative 0.04 times 5 plus 0.02 times 25 by 2 and obviously this is also negative, so this whole thing is inside, right, plus 0.05 t minus 0.25. And obviously this whole thing is inside the bracket, right. So what does this simplify to? this becomes 0.04 times 5 plus 0.01 into 25 minus 0.25. So, this is 0.2. So, this is e to the power of minus 0.05 t plus 0.2. This is something you would have derived in the first part of the question. This is basically Vt for t being greater than equal to 5, right? Let me verify if this is correct. So, this is a thing you would have derived as a part of the first part of the question, right? Now, let me get to that alternative solution that I was talking about, okay? So, alternatively, how you can do the PV that I was doing is this. You had a payment stream going from time 6 to 10, okay, and that's 10 e to the power of 0.01 t, okay, and dt. Now, you want to discount this directly till time 0. So, what you can do is for any arbitrary time t, because t is between 6 to 10, because t is between 6 to 10, it is automatically greater than 5, and because it is greater than 5, you can directly apply this discount factor to t, okay. So, what it becomes is, to discount the payment from time t to time 0 directly, it just becomes e to the power of minus 0.05 t plus 0.2, okay. You can just use this factor directly and this will give you your answer, okay. You do not even need to use this whole thing, right, extra thing. So, here what you were doing is you were taking it to time 6 first and then you were taking it to time 0. Here you are directly taking it to time 0 by leveraging what you have already derived in part 1. And mind you, here this discount factor is V0 comma t, okay. It is directly taking this payment stream which is running from time 6 to 10, and we are taking this payment at arbitrary time t, which is this part 10 e to the power of 0.01 t dt, and then we are directly discounting this to time 0 because t is greater than equal to 5. So, we can directly employ this discount factor which is Vt, which we would have derived in the first part of the question, okay. So, you can also use this sort of formulation, right, where you can directly discount this to time 0, and each of these payments will be discounted to time 0. Each of these payments which are happening between time 6 to 10 will be discounted to 0 by using this term from time t to 0, and then you would add over all the payments by just taking this integral from 6 to 10, and that is how it works, okay. So, in conclusion, basically whenever you are dealing with a payment which is happening at time t and you need to discount or accumulate, what you do is you take that payment assuming that it is at time t and then you discount it from there, okay. You do not discount from a fixed time 10 or 6 because the payment itself is happening at time t. This is what I did in the first way of doing it, where I was discounting it from t6 to t to 6, and that the same thing I am doing in the second way where I am directly discounting from t to 0. Okay, now let me look at the next question, which is again very similar but is related to accumulation, okay. Now, the force of interest is given. Let us look at the third part. A continuous payment stream received at the rate of 30 e to the power of minus 0.015 t units per annum between time 20 to 25, calculate the accumulated value of the payment stream at time 25. Okay, so now what will be the total value of this stream? The total value of this stream would be adding up from 20 to 25, that is when this stream is payable, and what is the value? 30 e to the power of minus 0.015 t and dt. If you would have just written this, this would give you the total value. But now you need to accumulate till time 25. From where? From the representative time t, okay, you need to accumulate till time 25. So it's e to the power of integrating from t to 25. Okay, and what is the force of interest that you will use? You will use 0.05 ds. That's it. This expression will give you the accumulated value at time 25 of this payment stream going from 20 to 25, right? Because again, this is a payment, representative payment, that is happening at time t, and I accumulate it to time 25, and then when I add all these payments from time 20 to 25, I get the sum of the accumulated value. Okay, so that's the idea. That's it for this video.